Hello, good afternoon. I am Vincent Wolfs. I'm a postdoctoral researcher at the University of Leuven in Belgium. And I'm also the general manager of a spin-off company called Sumaqua. And today I will talk about smart modeling for future-proof rainwater systems. And I'm going to talk about two different softwares, Sirio and SCAN. The first one is launched and the second one is currently under development. First, let's go to Belgium. In Belgium, as in any other country in Europe, we suffer from different problems. We, of course, have also the problem of having floods, especially in city centers. In some parts of the cities, we have very old sewer systems, hundreds of years old very often. And of course, they're not designed to cope with these high-intensity rainfall events. But we also have a lot of droughts. We have one of the lowest water availabilities in the whole of Europe, also like Poland, I just heard in one of the previous presentations. And on top of that, we have a very high degree of urbanization. So in Flanders, that's the northern part of Belgium, more than 14% of the entire area is paved, is impermeable. So that's a very high degree of urbanization, leading again to floods and droughts. And on top of that, we also have climate change, which further increases the risk of floods and droughts, of course. So we have to do something about it, and we want to build water-resilient cities in Flanders. And for this, we need to go for a lot of different strategies. We have to use adaptive infrastructure, of course. We have to go for win-win uses of open spaces, so multifunctional buffers, smart systems, as also introduced in the previous presentations. But we also need software and decision support systems to create strategic planning. And that's where the software that we developed comes in, so Sirio and SCAN. So that's basically the framework. So first, let's look at Sirio. Sirio is a software tool that we've developed to design climate-proof and optimal small-scale rainwater systems like buffer basins, for instance, or infiltration basins. But the unique thing about this is that it simulates long-term time series. So we're going to simulate hundreds of years of rainfall in just a few seconds. I'll explain that in a minute. So we've developed this at the university in Belgium, and in 1 year, because it's launched about a year ago now, it has become the standard tool for small-scale rainwater designs, and some companies here are in fact also using it. And as I said, the unique thing is that we can simulate 100 years of rainfall just in a second. So that's very easy to do. And then we can learn a lot from those data. We can do that because we've built a new simulation engine, which is very fast. Now, how can we use Sirio for some practical cases? We can use it for sewer designs, for instance. So we can determine how much buffer volumes that we should design, how often an overflow is going to occur, and so on. But we can also use it for rainwater harvesting analysis. So that's basically reusing rainwater. And that's becoming increasingly important and also increasingly applied in Belgium. So we can determine very precise how much water is available and what the optimal design should be to maximize the potential water reuse. We also use it for strategic water planning, so for industries, for instance, to create some water plans, also for cities. Brussels Airport, for instance, is also using it, and for climate adaptation. So we've built several climate change scenarios into the software, so you can also simulate those. And then you can see what's going to happen in the future with your specific design. How does it work precisely? I'll also show you an example in just one of the next slides, but I'm briefly going to go through the different steps. So the first step, you have to build your Sirio model. So you have to translate your design into some parameters in Sirio. I'm not going into technical details because that's not the point of this presentation, of course. But it's very easy to build such a model. So it's basically a reservoir type model and all the parameters are tangible, you can measure them. And then in the second step, you will simulate 100 years of rainfall, as I said, perhaps also including climate change. And then the third step is the statistical post-processing. So basically, the software then looks what happened in your system over the 100 years. So it counts how often do you have an overflow, how much water is going to infiltrate, and so on and so forth. So the latter two steps, those are done fully automatic. So what can we learn then from Sirio? Because of these long-term simulations, we can get a lot of insights. We can look at the mass balance, for instance. So how much water is going to infiltrate, how much is going to evaporate, how much is going to reuse, and so on. All the overflow characteristics from an event that occurs 20 times a year up to an event that occurs only once every century are directly visualized. Climate change impacts are also visualized, including the uncertainty, of course, rainwater harvesting analysis, and a lot of additional information into the dynamics of your system. But I'm not going to show that. So let's go to an example. This is a new residential zone which is currently being built in Ghent, a city in Belgium. And we received a design from a sewer company, from an engineering company basically. And design included some infiltration ponds, green roofs, buffers, and so on. So we were asked to evaluate that design and to check whether it's sustainable or not and if it could be improved. Now, unfortunately, I cannot do a live demonstration here of the software. That's not possible in this setting, so I had to include some print screens. So here you see the welcome screen of Sirio. It also has some instruction videos incorporated, so it's very easy to use. There are also a lot of examples available. Here you can see how we built a model. So on the left-hand side, you have the different blocks that represent your system, like a green roof, a buffer, and so on. And you can interlink them. And on the right-hand side, you have to specify the parameters. It's very intuitive to use. Here we see some of the simulation results. There are a lot of results available in tables, graphs, in reports as well. I'm not going into detail on all these different simulation results, but I just want to highlight a few of those. To begin with, this figure here on the left bottom side of the figure, this one shows us the mass balance, so where the water in your specific design is going to. And in this case, we saw that over the longer term, 40% of all the water in this region will infiltrate, and about 39% will be reused. So that means that 80%, if I sum the two, is going to stay there on the spot. So that's quite a sustainable design, but we could have improved it a bit further as well. Now let's look on the right-hand side. Here we have some more information. Here on this figure we see how often we will have an overflow and which volumes will occur. So that's already quite technical, but we can see here, for instance, that we will have an overflow event once every 5 years. And you can also see for higher return periods how much water precisely is going to overflow. And that's, of course, very important to determine whether such a design is good or if it's burdening the downstream system too much. So based on this, you can easily improve your designs. And we also checked if all the buffers that were being installed were also effectively being used. And this is a result of one of the buffers. You can see here on the y-axis the filling degree, so to which percentage that it is filled, versus how often it is filled. Here you can see that about 98–99% of the time the buffer will be empty, but that's also logical because it's not raining that often. But more strikingly is that this percentage, so it's 50%, so that means that only once in a century, your buffer will be filled for 50%. So the remainder, the other 50%, is never being used. So this buffer was over-dimensioned significantly. So you can build such a model in just a few minutes, and you can easily improve your design very much. That's also why it has become the standard software so fast. Now you can browse to this website, sumaqua.be/Sirio, and you can request a copy of the software to try it yourself. It's free, so you can always try. So to summarize the first part about Sirio, so you can easily improve your rainwater designs, you can experiment with different layouts, so you can be very creative in your design, think out of the box. You can design very fast, it just takes a few minutes. It also has a very fast simulation engine. And you can test a lot of what-if scenarios. So what if the infiltration capacity is, for instance, different from what you anticipated? How much overflows will you have in that case? And so on and so on. Now let's go to SCAN. That's the approach in the software tool that we're currently developing. And that's looking at a much broader scale. So SCAN looks at catchment scale. It looks at rivers, hydrology, urban systems as well, wastewater treatment plants in an integrated and also multidisciplinary way. We've already developed a modeling approach that is being used. It has also been published in some scientific journals. So basically, again, we have very fast models that enable a vast range of different applications. And it also uses some artificial intelligence. So basically, the modeling approach combines the conventional model structures with AI, machine learning techniques to get a much better estimation. And basically, these models are also self-learning. So from every rainfall event that passes, if you have some sensors in place, the model will be updated and will learn from the data that you measure. So they become more and more accurate over time as well. We've tested it in various operational settings. I'll show you some examples on the next slides. It can be included in any operational monitoring system. So the first application I wanted to show is an intelligent real-time flood control system, which is currently operational in Belgium. Here we're looking at the Demer Basin in Belgium. It's a basin consisting of some quite small rivers actually, but they flood very often and they're situated in a highly urbanized area. So that means that we have a lot of flood damages almost every year. Now, there are also a lot of controllable hydraulic infrastructures present, like this gate, for instance, which can move up and down, of course. And currently, these structures are being regulated using PLC, so that means simple rule-based controls. So it looks at water level at this location, another location, and based on that, it will determine its optimal position. But then we wanted to try, what if we link this with such an advanced model and look at forecasts as well? Can we then improve this system? So that's what we tested. So here on the left, you can see the SCAN model. This one is quite detailed. It has a bit over 1,000 calculation nodes, I think. But the main point is that it's very fast. So simulating years takes only a few seconds. It was actually calibrated to a hydrodynamic model, but hydrodynamic models cannot be used for these kind of applications because they're much too slow. And the second thing that is important is its accuracy. So on the right-hand side, you can see some graphs of simulation results and observed data, and they match almost perfectly. This is from an offline simulation. So then we've built a SCAN model, and now we've linked it to some optimization algorithms to determine the best position of all the gates in our system. And we could see that it can easily improve your control structures very much. So we've simulated an event that occurred a few years ago, and that event has led to 3 million euros of damage. Now, if we apply this smart system together with the SCAN model, we could reduce the damage by 1 million euros. So and the important thing is that we do not need to build any additional hydraulic infrastructure. So we just use what is present already, but in a much more efficient way. That's how it works. The second application to conclude this presentation is the first intelligent green roof that we've built in Flanders. It's part of the Brigade project. That's a European Horizon 2020 project in which we're testing different innovations. We're always looking for new innovations to test, by the way. So if you have an innovation related to climate disaster resilience and you want to test it on a European scale, you can always contact us, and then we can also test your innovation. Currently, we're testing about 50 different innovations. So this green roof is one of those. Basically, it's just a conventional green roof, a regular one, with some extras. First of all, we have a storage tray at the bottom of the green roof, so we can capture water, we can control the water inside the green roof. And secondly, the outlet of this tray is also controllable remotely. So basically, in dry periods, we will try to capture as much rainwater as possible. So that means that the vegetation has much more water and will survive drier periods for a longer time. And then in the opposite, when a high intensity rainfall event is predicted, we can quickly empty this green roof so that more water space becomes available, and then we can capture the incoming rainfall event as well. So that's basically the setup. So the goal is to mitigate the rainfall peak flows, to reduce the runoff volumes, and to optimize the water availability. So we've built this in the city of Antwerp in Belgium in one operational case. And this is then where a scan comes in. Now we're going to upscale the results to the whole city. So we're going to see what happens if we would employ a lot of these intelligent green roofs across the city of Antwerp. Will it have an impact or not? So we can then check, for instance, the impact on urban floods, but also on city heat stress. We can determine the optimal outflow regulations of the green roof using SCAN, and so on and so forth. So basically, these were two applications of the SCAN platform, which is currently under development. So that was it. Thank you very much for your attention. If you want a copy of Sirio, just browse to the website, or you can send me an email. Or if you have any ideas for collaborations in European projects or anything, you can always contact me. Thank you.